Yeah, whoever is possible, turn on your video. That's very helpful for me. I'll also enable sharing screen because that will help us to do. Yeah, please share your screen. Sorry, share your turn on your video. And if you don't have noise coming from your side, you can turn on your audio also. Hello. Hmm. Hello.
Sir.
Yeah.
Yes, sir.
Yeah. Turn on your video. Okay. Rohit
Sir,
Jajara. Hi.
good morning, sir.
Good morning. Yeah. So some more people turn on your video. That's. Can you see my screen?
Yes, sir.
All right. Okay. So today's class we are going to get introduced to scheme. All right.
Okay.
Okay. So did you all install scheme in your machine?
Yes, sir.
Did you?
Yes, sir.
Okay. Did you try it out? No. Okay. That's fine. That's fine. So the way you start, you have to install scheme from either just search for MIT scheme. There are many implementations of scheme. Scheme originated in MIT in 1970s, late 1970s, I think, early 1970s. And there are several implementations of scheme. The most recent implementation is something called a Racket. Uh, Racket has a IDE called Doctor Racket, but Racket has some differences from the variant which we use in the book. So that's why it's preferable to use MIT scheme. Okay, Racket has an IDE, integrated editor. So um, yeah. All right. So the way I could start scheme from once it is installed, you just type scheme, and then this brings something called REPL. Okay. What is REPL? REPL stands for read. Anybody? Any idea? REPL stands for read eval print loop. Okay. So you have when you start Python, uh, you type Python and then it brings up an REPL of Python, okay, in which you can evaluate expressions. So similarly, when you start scheme starts it's on REPL REPL. Okay. In this REPL, what it does is that it reads what you type and evaluates it and then prints it, and then it goes on a loop. It waits for you to enter the next one. Okay, that's why we call it read eval print loop. Okay, so what are the basic data types of this one? So if you type 2, 3, etc., it's a number. 23.2 is a number. So this is how you type numbers. Then for the moment, we won't look at strings. Sharp T is the Boolean value true. Sharp false is the Boolean value false. Okay. So now previous class also I told you how to do the specific thing about Lisp. What is the most specific thing about Lisp? We saw it last class. Everything
Backcode.
is, pardon?
Backcode.
Uh, yeah, backward is a bit too advanced. I was thinking more like everything is in prefix form. Yeah. No, I should. Let me type it in notes. Everything in Lisp is in prefix form. Okay, what does that mean? That means that you will always write function name, argument 1, argument 2. This is the way everything in Lisp will look like. First, you will write the function name, then you will write argument 1, argument 2, argument k, up to argument k. Okay, so that's what I mean by uh, everything in Lisp is in prefix form. Let's see an example. Somebody is making too much noise. Unless you are talking, please turn off your audio. But I would prefer really to see your video, because that helps me to actually get some feedback, whether you are able to understand what I'm saying or not. So if it is possible, please turn on your video. Yeah. So if I write plus 3, 4, I actually am writing the function plus and then 3 and then 4. And if I want to compare equal to 4 and 5, it will give me false, because it says it actually checks 4 and 5. Actually, plus can be used with many things. You can write any number of things. It's
Sir,
not
your
just
screen
two.
sharing is off.
Oh, screen sharing is off.
Yes, sir.
No, I am able to see it actually.
Now,
Yeah, yes, sir. We can see.
yeah. So I write plus 3, 4, 5, 6. It will just sum up all of them. Okay. If I write minus 5 and 2, minus 5 and 1, it will give me 5 minus 1, 4. So the first argument will go to the left of the expression, and the rest will be on the right. Okay. Minus 7, 3, 2, 1 will be 7 minus 3 minus 2 minus 1. So that's like 1. Okay. Hello. And less than 5, 4 will be read as 5 is less than 4, which is false. Okay. All right, that is how we write expressions. Now let's write, we are learning the first complication of the language, which is the define. When I write define x10, okay, what it does is that it actually says x is the name define name value, assigns value to name. Okay. I'm not calling it variable yet. Okay. Because where it is really like names. We are people, we have names. We don't change our names often. Okay. We are named for once, and then for the rest of our life we use the same name. Similarly, in functional programming languages, changing state is not at all recommended. Okay. There are languages like Haskell. In Haskell, it is not possible to change the state. There is no reassignment of anything. You can put x equal to 10, and then next time when you say x equal to 11, the compiler will say, what are you talking about? Because you told it x equal to 10. Now you can't say x equal to 11. But in Lisp, most of the other programming language, functional languages, changing of state is allowed, but it will be used very sporadically. Okay, very rarely. I mean, it is even in this book you will see that we will use the real assignment in that sense much later on, only when we actually need the state. So that's why we call it name. Okay. Now the most important thing is that define keyword can be used to define functions. Define function name. So for instance, I want to define factorial. So the way I will do it is as define factorial fact, and then I will say x, and then I will write what needs to be done by the factorial. For instance, if I want to be factorial is pretty difficult to check. Let's write a Boolean function. Less than 5 of x will be less than x 5. Okay. So you see this, what I have done, this expression is of the form define function name, arguments, argument 1, argument k. Then I have here is body. This is the common pattern of I'm defining a function. Define a function and the arguments, and then I'm saying it's an expression. So this function is nothing but this body. Okay. Let's also see if then else. Then we will be able to write functions. So if I want to write factorial, the way I'm going to do it is as define factorial of x is now, I'm going to say it as a body. What is that body? If expression has this following form: if equal to x 0, if x equal to 0, then 1, otherwise multiply fact why is it coming this way? 1 second. Okay, that is my factorial function. Now let's try to understand what I have written. So I have written define factorial of x. This function factorial of x is what I'm defining, and I'm saying it's an if statement. What is the syntax of if statement? If condition uh, okay, this is how if statement is. Can somebody explain what does this mean? Hello.
So if the condition is true, then argument 1 will be executed and returned, or
Yes.
else argument 2.
Yeah, exactly. So if the condition is true, if the condition has to evaluate a true or false value. And if it is true, then argument 1 will be returned. Otherwise, argument 2 will be there. So let's not use the word executed and returned and things like that. These are all going to be expressions and they are going to be evaluated. Okay. So if this is an if expression, in the C language world, you will say if statement, but here you would say if expression. So the value of this whole expression is, if the condition evaluates to true, then argument is the value of the expression. If the condition evaluates to false, then argument 2 is the value of the expression. Any questions? Evaluate if condition evaluates to true, weights to sharp t. Sharp t is our true. Then arg1 is the arg1 is the value of the expression, else arg2 okay. That is the meaning of if. So now let's let's try to understand this function factorial of x. Define factorial of x is if x equal to 1, yeah, that's how you read it, x equal to 1, then you will say 1. Otherwise you will say multiply, if it is if x equal to 1, then the value of the expression factorial of x is 1. Otherwise multiply x and factorial of x minus 1, but I have written them in prefix form. Okay. Hello.
Yes, sir.
Yeah, somebody's fan is missing. Okay, now the one thing I've done one thing. The thing which I have done is I have written the arguments to the if expression one by one below. Yeah, if has three arguments. One is the condition. One is this condition evaluation expression. One is this argument expression. Argument 1, argument 2. There are three arguments to if. I have written them below one by one. Okay, this is called pretty printing. Pretty printing. What does pretty printing mean? Write expressions, arguments to a function one by one below one another. Okay. And so therefore, if I want to look at what parsing this if statement becomes very easy for me. This is the condition, this is the argument 1, this is the argument 2. And if factorial has more than one arguments, then I will write them one by one. So it will be like one by one by one by one. Yeah. So it becomes easy for me to read. Okay. So now, can we write how to find sum of k numbers? Can we write define sum k? Can somebody tell me how to do this? Or can you do it in your machine? Define sum k. So what should sum k do? Sum k should be 0 plus 1 plus dot 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 plus k. Okay, this is what I have to do. Devyani,
Yes, sir.
are you doing it?
Yes, sir.
All right. Yeah, can somebody show me your screen once you are done?
Hello.
Yeah, who is this?
Yes, sir. Siddharth here.
Yeah, show me Siddharth.
Just a second, sir. Sir, it's not allowing to share the screen.
1 second.
You cannot share screen while other
Yeah,
participant
yeah.
is sharing.
No, okay, can you share now?
Uh, 1 second, sir. Sir, is it visible now?
Yeah, it is visible.
Yes, sir. Sir,
Okay,
this
okay.
line.
Yeah. Show me. Move, yeah.
So
Define
on,
sum k. Yeah, if k equal to 0, then 0. Otherwise, plus k, sum k minus 1. All right, very good. That is how it is. Okay.
yes, sir.
Yeah, all right. Thank you. Did everybody get that? Let me, I will just redo it here. Siddharth solution. Yeah, Siddharth, I will share my screen now.
Yes, sir. I have stopped sharing.
Okay, thank you. So Siddharth solution is this: define sum k if will be this expression. What is that expression? It's an if expression. If equal to k 0, then I will come here and I will say 0. Otherwise, it is plus of k and sum of minus k1. Okay, is it clear?
Sir, I had a question.
Yeah.
So, like, can we implement if without using these conditions? I mean, in general, is it
No, we
possible?
cannot. We need some form of branching. Okay, and without if statement, you need if statement. You can't write if statement on your own. Okay. Yeah, you will need that. There are very few basic things you need to do. Okay. So this is how you do it. Now let me say one more thing. Right now, so Siddharth had this problem. I couldn't write this in the RIPL. Yeah, 1 second. Yeah, I couldn't write this in the RIPL. So to write this in the RIPL, I mean, if I would, it would be easier for me to write this in a profile and then load the file. Okay, let's see that also, and then we will move to more advanced things. So I want to write that function, this one. So I create a file, sum dot scheme files. Usually we write with the extension SCM scheme. Okay, sum dot scheme. So I'm going to, so if you use one of these editors, either Vim or Emacs, it will be much easier. Anyway, you have to learn either Vim or Emacs if you are for your happy life. Okay, and here I come and I define sum k if equal to k1 0, otherwise it is plus k and sum of minus k and 1. Yeah, so I write it into a file called sum.scheme. Now I go to my scheme and I type load in the same bracket. Yeah, bracket load. I'm going to execute a command called load. Then I write sum.scheme. Okay, then I have loaded the sum. Now every function in that file is available to me. So I can write sum of 5. That will give me 15. 5 plus 4 plus 3 plus 2 plus 1. Yeah, clear? So that is how you write into a file and then load it into the this one. So yeah, and yeah, if I want to exit the REPL, I just put Control D. Okay. All right. So in the first chapter, so what all things did we learn so far? Can somebody repeat? Okay, some Jarrett has sent to me define sum equal to okay, some sir, I using racket. Is it okay? Yeah, it's okay. But in racket, they if the more general form is called cont, and the cont syntax is a bit different. So in all these Lisp variants, the most popular one is closure. Even in closure, there are significant some slight differences in syntax, but underlying all everything will be the same. Okay, so you can use closure or you can use scheme. It's all fine, but I will be using scheme because in the book it will be scheme. Okay.
So I'm using a scheme only, scheme language and in bracket SICP.
Yeah.
So am I?
Yeah. That's fine. That's fine. So how are you using it in Racket? You actually loaded SICP.
Yes.
Yeah. So that's one possibility. You can load SICP. So where is it? You come here. Okay. I have Dr. Racket here. I load Dr. Racket. Okay. And I come here. I open Dr. Racket. Can you see my screen? Yeah. And I come here and you load SICP here. Yeah. Yeah. You load SICP here and then we can do the same thing here and we will get the answers here. And so here you go and you run. Now, what is what do you have to load here? SICP or
So SICP is sufficient.
SICP?
Yeah, that is. But you need to download the SICP, sir.
Okay. So I probably have to download. Okay, so then I won't attempt it today. Some other day. But you guys can try it and tell me what to be done. Okay, now let's move forward. So in the first chapter, what you are going to learn mostly about is whatever I have shown you now. Okay, and then you will actually see the square roots method of computing roots, and then we will talk about recursion and tail recursion. Let's talk about that a little bit, and then so the plan is that we will do in the class. We will do a review of whatever is going to come or whatever has done, but you have to read the book and you have to go through the slides on your own. Okay. Okay. Okay, so let's come back. Let's come back to notes. Okay, one thing we notice is that there are no while loops, while, for, etc. in scheme. Okay, these are called iteration constructs, loop constructs, or iteration constructs for iterations. Okay, there is only what? What did we just use to define sum and factorial?
Because
Recursion.
There is only recursion. Okay, so that will be the first major difference in functional languages. In functional languages, we won't have any while loops, for loops, etc. We'll only have recursion. Now, but there will be a difference between recursion, but iteration can be achieved via recursion. That is what we are going to see today. Okay, let me write that factorial function this way. I'm going to define factorial in a new way. I'm going to say defining iteration. Okay, I'm going to define fact iter x will be, I'm going to define not just x, I'm going to say fact iter x product and counter. Okay, and my plan is this. My plan is to say I will start if I want to compute factorial of some k, I will start with 1 and 1. Okay, and in the next step I will go to fact iter of k and 2 and 1 and 2. In the next I will go to where fact iter of k, and I will multiply this counter to product and increment the counter. That's my plan. Okay, so it will become 3 and so on. Get it? Are you getting what I'm aiming at? K, 6 and 4. The next step I'll go to fact iter k, 24 and 5 and so on. So, and whenever the counter becomes k, whenever counter exceeds k, I will stop and I will return product. Are you getting what I'm saying? Who got what I said? So for instance, if I want to compute factor iter of k, k equal to 5, if k equal to 5, I will stop in the next line. I will stop 5, 120 and 6 and return 120. Are you saying, no, let me write the code, then we will discuss. If greater than counter x, if x is greater than the counter, then I'll say prod. Otherwise, I'll say fact iter x Can somebody try to explain what is going on here?
So I can try.
Yeah, please.
So essentially what it is ki prod holds the factorial of counter minus 1.
Yes.
So
Yeah.
what is prod? It is just repeated multiplication of 1 into 2 into 3 up till the counter, not
Yeah.
counter included.
Okay.
And
Yeah.
when we use the factor of x prod counter,
Yeah.
what we do is we multiply counter to the prod.
Yeah.
So this will become the factorial of counter.
Yeah.
Prod will become factorial of counter.
Counter. Yeah.
We will stop when counter is greater than x
Yeah.
because that will be when
Yeah.
prod is equal to 1.
Yeah. So now if I want to compute factorial of 10, I can just write fact iter 10 1 1 will give me the factorial of 10, isn't it?
Yes.
So this form of iteration has a difference between the previous form of iteration. But the previous factorial we have written and this factorial we have written, there is a difference. What is that difference? It's a very crucial difference. And this recursion we will call iteration, and the other recursion we will call normal recursion. This is what we call recursion. I mean iteration. Can somebody tell me what could be a difference between this factorial function and the previous factorial function we have written?
Hello.
Yeah,
So for the previous one, there was a computation at each recursive call. Whereas in this case, whatever happens at the last recursive call, and the other recursive calls basically just pass it on. So
very
similar
good.
to an
Who is this? Who is this?
So Devyani.
Okay, very good. So what Devyani is saying is that if we look at the previous factorial function, okay, I'm going to one second. So this was our original factorial function. Yeah, and okay, I have loaded both those factorial into my scheme. Now there is a command called trace fact, which will actually try to which will show me the trace of this function call, and I'm going to call fact of 4 now, and it will show me how fact of the function call included in fact of 4. Okay, now it says that it actually entered the factorial function with the argument 4, then it called the factorial function with the argument 3, then it called factorial with the argument 2, and so on, and then finally it returned from 1 and 2 and 3 and 4. Okay, and then I got this 4. Okay, and if we look at the other factorial function, it will do something similar. So recursively they are the same, except that what Devyani was saying is Let's look at these two functions once more. Okay. So here, if I want to compute, if I try to expand factorial of let's say 3, okay, what I'm going to do is that my factorial of 3 is actually this expression. Okay, this expression. Now this expression, when I evaluate this expression x equal to 1, it is false. So therefore, it becomes star 3, then fact of 2. Yeah, this is what it becomes. When I try to evaluate the expression fact 3, it becomes evaluating the expression multiply 3 and fact of 2. But fact of t I have to evaluate again. So it becomes multiply 3 and multiply 2 and fact of 1. Yeah, this becomes this expression. There's the one more. It becomes this expression. Now multiplying, evaluating this expression becomes multiplying 2 and 1. Yeah, and this becomes star of 3 and 2, and this becomes 6. So this is how Lisp will evaluate this factorial function. Is that clear to everybody? This is very crucial. How Lisp evaluates a function. It is actually not executing or anything. It is actually evaluating expressions. It actually rewrites the expression. This is called substitution model. Model of execution. Substitution model of execution means that to evaluate an expression, you just substitute every expression with the corresponding body. Okay, so here fact 3 becomes this if expression. I have not written the complete if expression, but immediately I can evaluate x, substitute for x, so x is 3, and then I can reduce that expression. So I have only written that part. I have not written the complete substitutions. Yeah, I have only written the relevant parts for us. So fact 3, and then it becomes star 3 fact 2, then it becomes star 3 star 2 fact 1, and then finally fact 1 evaluates to 1. So therefore it expands. So when I am trying to evaluate fact of 3, it actually, the expression actually expands.
It's 11 o'clock.
And then it shrinks. Yes. Is that clear to everybody? So if I want to evaluate one fact of 120, I will get a huge expression initially. 120 into 121, 119 into 118 into etc. all the way up to fact 1. Only then it I can this one. I can actually evaluate the expression in one shot. Isn't it clear? Is it clear? Any questions? But let's look at this expression. So this expression, how is the evaluation happening? Fact of, let's say fact of 311. It becomes what? Fact of 311 becomes what? Fact iter, sorry. Fact iter of 311 becomes?
Fact iter of 312.
312, which becomes? Fact iter of 323, and then it becomes fact iter of 364, and at this point it just returns 6. Yeah. Is it clear? So basically what happens is that in this case, there is nothing. In this case, what happened was that when fact 3 was evaluating, I had something to be left done by the fact 3, which is multiply 3 and fact 2. Only after computing the fact 2, I could return, I could exit that function. That function was holding on to something to be done yet. In this case, this is called tail recursion. Tail recursion. The value, what does that mean? That means that the value of the function of a recursive call is the end of the recursion else is propagated. Now, I mean, what should be the, let me search in this book. Or let's say recursion can be done in constant space. Let's take that as the definition of recursive call, tail recursion. So in usual recursion, what happens is that a function function call, to implement a recursive call, you have to have stack frames. You will save all the functions data, its variable bound binds and all these things in one stack frame. And for the next recursive call, I'll place something on top. For the next recursive call, I'll place something on top, because the functions cannot be all the data of the current function call cannot be eliminated. There is something still left to be computed by that. So I have to save that. On top of that, I will put the next function frame. On top of that, I'll put the next function frame and so on. Okay. In the case of tail recursive call, what could be done is that the current function call, what should be returned by the current function call is actually computed by the next one. So therefore, I could just remove this and place the next stack frame at the same place. Okay. Now, therefore, you don't need extra space. In the original factorial function, you will need as much space as the number x. Linear space, you will require linear space in the size of x to have that function call, because this expression is going to expand. On the other hand, in the case of tail recursion, you don't need this. Now, why do I say this? Because a scheme does not have, we already observed that scheme does not have any iterative constraint, doesn't have any while loops or for loop, etc. So therefore, you have to use recursion. But when you use recursion, there is a problem that you will need extra space. You will need space which grows linearly in the number of steps, in the number of input argument, the size of the input argument. But if you have iteration or tail recursion, then essentially you can actually perform operations, looping iterations in recursive, in constant space. And scheme, one of the biggest one of the new programming language features introduced by scheme at that time was something called continuations. Okay, there are three styles in which you could do recursion. One is the recursion which we have seen, the first form, the normal recursion. Second is tail recursion, and the third is something called continuation passing style. Okay, and scheme, it is a bit difficult, which is actually a way. What is continuation passing style? It's called CPS, continuation passing style. Continuation passing style is a technique used by compilers to actually, you could write, you see that it is easy for us to write a recursion in this form. In the first form we have written, it is easy for us to write that, because it is more like the natural way in which you write programs. But you also see that it is more economic to write programs in the second form, but it is more difficult for us, even though it is economic. So what what scheme automatically does is that when you write a function in the first form, scheme compiler will convert it into the second form, and then it will execute that. Okay. Now, one of the things which is done in this book is actually writing a interpreter for scheme in scheme itself. So scheme is an amazing language in which, in the first course in computer science, you will be able to write an interpreter for scheme in scheme itself, which is rather amazing. That in a language, like in a language, you in the first course in computer science, you are able to write the interpreter for the language in the language itself. We will see that. Okay. So this is what is tail recursion. Okay. And why it scheme in the continuation passing style, scheme actually converts the normal recursion to tail recursion. So today we will learn what is tail recursion. And so they basically one thing which we learn is that tail recursion is more useful and and faster because it consumes less space. Consumes less space. Faster. Okay. And in the presence of tail recursion, in the presence of compiler, providing tail optimization, it's called tail optimization, iteration, constructions for iteration, are not needed. All right. Any questions?
Sir, I had one question.
Yeah.
Sir, you mentioned that in scheme we don't have variables; we only have names. So we cannot assign one thing to like x equal to 10, then x equal to 11.
Yeah.
But in this recursion, we are using the counter and we are updating it. So how does that become possible then?
So you are asking whether when I say counter plus one, so these are yeah, you are
the
saying
value is counter only.
Yeah, but that is not really yeah. So what you are actually talking about is um, the answer to your question is scope. Okay, the answer to your question is what we call scope. So what happens is that when I have a variable, when I have a variable, when I have a name, okay, that name is not within a program. It's not like one address book. Okay. So what happens is that we have something called scope. Okay, maybe we can discuss this on next class. Anyway, we'll need to discuss that because we will have something called lexical scope and dynamic scope, which we have to discuss. So what does scope mean? Scope means how much your name extends to. Okay, within your program, you might have programmed in C. One name at different places of the program can, even without reassignments, one name can at different places can mean different things. For instance, I have a function f, and within that function, I write int x equal to 10. Okay. And another place I write g, and here I write int x equal to 20. Okay. Can you see this? Hello. Yeah. Now,
Yes, sir.
this is not reassignment. I'm not taking x and putting 10, and I'm not taking the same x and putting 20. What happens is that these are at two different scopes. These are at functions in C implement their own scope, in the sense that this function has its own, you can think of it as an address book. This function has its own scope. This function has its own scope. So within this scope, x is unique, and I'm not reassigning this. This x and this x are at two different scopes. Okay, agree? This x,
Yes, sir.
this x and this x are two different scopes, so I'm not actually reassigning them. Similarly, when I'm doing a recursive call, this counter and this counter are at two different scopes. There are two different instantiations of the same function, but they are two different instantiations, so they are at two different scopes. Okay.
Okay, sir.
All right. So within the same scope, if you are actually reassigning a variable or a name, that is when we call it a reassignment. Okay. Within the same scope, you have to be in the same scope. Okay. Now the standard definition of scheme is lexically scoped Lisp is what is the standard definition of scheme, because Lisp usually does not have lexical scoping of this one. We will actually see what is lexical scoping in the next class. Lisp does not have usually lexical scoping. Lexical scoping was implemented first time by a programming language called Algol. Algol is a daddy of most programming languages which we see today. See all these languages, and Algol first introduced this idea of scoping. Before that, there was no idea of scoping, like static scoping. And since then, most of programming languages, so your natural intuition about what is the value of programming language, what is the value of a programming of a variable, is what is static scoping. You look at its environment and you deduce from there what is the value of this variable. Okay, and in today, static scoping or the normal scoping is the most usual form uh, of uh, of uh, this thing of scoping. But there are some counterintuitive places where you will have. I'll give you an example. Everybody, so there are some Python. Some people know Python here. Okay, let me ask you this question. Def f x. Okay, can you see this code? Can you see this code? It's a little bit of Python code. So I have a function f which takes one argument x, and this function defines another function within it called g of y. Okay, and what does that function do? That function returns x plus y, and then this function f returns this function g, which takes one argument and returns x plus y. Okay, and I have a function h which calls f with 10. So what will I get? Let's call it a. I have a function h which calls. Let's get rid of this. Imagine, this function is clear.
Yes, sir.
Okay, x equal to 20. What will be printed is my question. Can you see this function f of x def g of y return x plus y return g, and I call this function f with value 10. So it will actually return me a function g which will return x plus y. So this function g has an x in its scope. And then I reassign x equal to 20, and I print a of 10. What will be printed? What will be printed? Will it print 10 or will it print 20? What will be printed? Any guess? Anybody?
Sir, A of 0 should print 10.
A of 0 should print 10. Why? Why should it print 10? Yeah, so it is what you're saying is right, but you have an intuition about what should be printed. Yeah, that intuition, we have to make sure, we have to make clear what that intuition, that is the intuition of static scoping. But can you tell me tell me why you think it should print 10?
20 is a global scope and 10 is local scope.
20 is the local scope and 10 is the global. 20 is the global scope and 10 is the local scope. Can you be a little more precise? It's not exactly that answer. Anyway, you think about it, you find me a good answer, and then we will meet on Wednesday. Okay. Before we meet on Wednesday, will you be able to read the chapters 1.1 and 1.2? So 1.1 and 1.2 and the corresponding slides, I'll send the slide list. Okay. So you'll have to read 1.1 and 1.2 before we meet on Wednesday. All right. Okay. And do the exercises also. I'll send the exercise also. All right. Thank you. Bye. Bye.
Thank you, sir.
Yeah, bye.
Thank you, sir.
Bye.
Yes, thank you.